Now we want to talk about how those bonds actually form, and we're going to use the idea of Lewis theory. So what we want to get into is talking about the idea of Lewis theory. And Lewis theory is a model of how and why bonds form. We're talked about atoms. We know how to characterize the types of bonds. So what about why do bonds form? If two atoms are going to form a bond, what's it going to look like? And so Lewis theory gives us kind of an underlying model of what goes into that. And the basic principle that underlies all of Lewis theory is the idea that pairs of electrons are most stable. So everything is going to be about forming pairs of electrons. This actually goes back to, if you remember that idea of spin that we talked about, that electrons can have an upspin or a downspin, and two can go in an orbital. That's what's kind of stable, is when you have the up and the down paired up together, that works best. So with that idea, when we make covalent bonds, they're going to be composed of shared pairs of electrons between pairs of atoms. So two atoms are going to come together, and they're going to share a pair of electrons. Share electrons one pair at a time. And so this sharing is going to happen when we're going to facilitate, forming these bonds to share pairs. And the bonds are going to form such that atoms overall will gain 8 electrons in their valence, right? They're going to share electrons. They're going to now have more electrons around them. This 8 corresponds to what we've called a full valence, and is reflective of what we call the Octet Rule. So that Octet Rule, right, is the idea that all of our noble gases don't form bonds. And the reason why these noble gases tend to not do any chemistry is because their electrons are already in a stable configuration. They have 8 valence electrons in each of them. There's something special about having those 8 valence electrons. It's a full shell, all of our full subshells, right? The S has the 2 and the P has the 6 electrons in. So that's stable. You don't need to exchange. There's kind of nowhere to put electrons. You don't need any extras. You don't have any holes. There is one exception to this. That's helium, where helium only has 2 valence electrons. That's why it's on Octet Rule and not the Octet Law. So helium only has 2 electrons, but you'll note it still is a full shell. The N equals 1 shell where helium has electrons, there is no P subshell to fill up, right? So you don't need those extra 6 electrons, but helium still, it doesn't follow the letter of the rule of having 8 electrons, but it follows the spirit of it to have those 2 electrons in its valence. So our end goal is to look at molecules, but it's probably a good idea to start with atoms. Let's think about what the Lewis symbols for atoms are. Okay, and so the idea here is we know we're looking at valence electrons. So what I'm going to do is I'm going to write my individual atoms and then indicate how many valence electrons each atom has. And these are not atoms within a molecule, just isolated atoms by themselves. So if I think about period 2, so this is the second row of the periodic table, and I just start from the left to right, I could start with lithium, and I know that it's the first column of the periodic table, so it's only going to have 1 valence electron. So if I want to write its symbol, I know I'm going to start, the base is going to be its chemical symbol, so for lithium that's Li, and I'm going to put 1 dot, right? Because it has 1 valence electron, I'm going to use a dot for that. I'm not interested in representing the core electrons because those aren't participating in any of the chemistry. I'm only going to put 1 dot on my lithium. So the next atom is going to be beryllium, and it has 2 valence electrons in the second column, the second group, 2A, and so it gets 2 dots. One of the things you'll note is that those 2 dots are not together. They are opposite in this case. They are just not paired up yet. And in general, with Lewis symbols, we don't pair electrons until we need to. So what we wouldn't want to do is have the beryllium with the 2 electrons next to each other. If we think back to that Lewis structure, that nitrogen atom had those 2 dots corresponding to a non-bonding pair of electrons. We don't want to do that yet when we're talking about atoms until we need to. So keep going. Boron is next, has 3 electrons. We're still not paired up. Those electrons are independent of each other. 3 kind of single electrons around the boron atom. As we step up carbon, we've gotten to 4 electrons in group 4. And as we keep going across, next to carbon is now group 5, and we hit nitrogen. And so nitrogen has 5 valence electrons. And so now we can see that there are 2 paired up on the top. This is where we said we were going to wait until we had to pair them. This is where we need to pair electrons. If I look here, I have these 2 electrons paired together. I call that a lone pair. That may seem a bit oxymoronic. Lone in this case refers to a single atom. So lone refers to the atom, pair refers to the electrons. So there's a pair of electrons that is located on a single atom. This is basically just in contrast to a shared pair, that would be the opposite, which is those sorts of covalent bonds. So lone means one atom with two electrons paired up together on it. Okay, so there is nitrogen. If I go up one more is oxygen in group 6 that has 6 valence electrons. And now we can see here that oxygen has 2 lone pairs because I only have basically 4 places to put electrons. I have to start doubling up. If I go to fluorine with its 7 valence electrons, it has 3 lone pairs and then the 1 single unpaired electron. Next, after fluorine is neon with its 8 valence electrons, its full octet, and now it has all paired up electrons. And we can kind of start to see what we mean by full octet. There's nowhere else to put those electrons. We have 4 places. They each can put 2. So now neon is full. And I do want to note, these relative positions of the dots around an atom don't matter. If that lithium has that 1 valence electron, it could be on the top, it could be on the left, right, bottom. What's most important is how many electrons you have and how they're paired up. That you don't have any pairs until you get to 5 total, and that you keep them those 4 separate pairs as you work your way up. So the relative positions around don't matter. What does matter is the chemical symbol, right, and the number of valence electrons and how they're paired up around the atom, not necessarily any sort of position. All right, so if we wanted to, say, draw Lewis symbols for atoms, so, we want to get practice kind of looking at these things. And if I'm drawing Lewis symbols, the real first question is always going to be, how many valence electrons does the atom have? And if we're looking at, that we can use the periodic table, look at what column it's in, first, second, 1A, 2A, 3A, 4A, just take that number. That's going to equal the number of valence electrons. And then it's just a matter of placing electrons around the atom and following that pattern. 1, 2, 3, 4, 1, 2, 3, 4, pairing up only once we get that 5th electron, right? Only pair when there's more than 4 total. So the first atom is sodium, right there. Sodium is in group 1A. We can see right there. So it has 1 valence electron. Since it has 1 valence electron, the Lewis symbol is Na with a single dot. There's not really much we can do. I can put that dot wherever I want, but it's just a single dot. All right, next I have germanium right here. Germanium is in group 4A, so it has 4 valence electrons. So when I put now my germanium symbol is Ge, and when I do those dots 1, 2, 3, 4, all around the outside of the atom, and we can see they are not paired up. If I have 4 or less, I do not pair up the electrons. I just put them out as single dots around the atomic symbol. So if I go to chlorine, now over here, group 7A has 7 valence electrons. This is greater than 4, so decent chance we're going to get pairing up. And we can see that it's, we only have 4 places to put them, but we can see that to get that 5th, 6th, and 7th electron, we have those 3 pairs that show up around the outside of the Lewis symbol. Bromine, Br, is right here, again in group 7A, so 7 valence electrons. So if we go to put those out, we know that we have 4 places. We can do the 1, 2, 3, 4, but then we have to make 3 pairs to accommodate that 5th, 6th, and 7th electron. So we can see overall that this bromine has those 3 lone pairs and then the 1 single electron left over for a total of 7. Next one, iodine is right here. That's in group 7A, and we can see that means it has 7 valence electrons. If we look at our Lewis symbol, it's going to be an I with its 7 electrons in 3 lone pairs and 1 single unpaired electron. And so one of the takeaways, if we look at that chlorine, bromine, iodine, we're all in group 7A, and they all have the exact same symbol except for the letters in it. because they all have the same number of valence electrons, right? This is the idea that atoms in a given column have the same valence electrons, and as a result, they're going to do the same type of chemistry. And that's what we're going to see here, that they have the same sort of patterns of electrons around them, and so they're going to follow the same. And actually, all this is true for all columns of the periodic table. All the atoms have the exact same Lewis symbol except for what letters are in between, because they all have the same number of valence electrons. And so practically this means that you figure out one sort of the rules for filling the valence electrons around an atom for any period, and you're good to go. Yeah, you can just figure that out. But more importantly for chemistry, this means that for a given column, all of my atoms are going to have the same type of chemistry, right? This is the idea we've seen again and again, that a group all has the same sort of chemical properties and does the same sort of reactions, all that sort of good stuff.